So in this session, we'll discuss mainly about the ionic bond and how to calculate the lattice energy. That's the main focus for this class. So first, what is the ionic bond? The ionic bond, the bond which is formed by a complete transfer of electron. So the metal has a tendency to lose electron, where the non-metal has a tendency to gain electron. As the metal lose electron, it will get a positive charge. Non-metal gain electron, negative. And the electrostatic attraction, the attraction between the ions, what we call that as, a ionic bond. So when these ionic bonds are formed, bond forming is always exothermic. So when these ions come closer to each other, this result in an emission of energy. Energy is released, and whenever energy is released or energy is given out, that kind of reaction is known as exothermic. So bond forming is always exothermic. So energy release, when ions come closer, as they release energy, they lose their energy, and we call this energy as a lattice energy. So this lattice energy, when ions arrange themselves in a regular pattern, release energy, we call that as lattice energy. So when we compare the lattice energy depends on two main factors. Number one, it depends on the size of the ions. For a higher lattice energy, the size of the ions should be small as possible. So they will be closer to each other. And charge on the ions should be large as possible. They should have a greater charge so that they will have a greater lattice energy. So example, we have two ions. One is sodium, another one is chloride, and lithium and chloride. Lithium will have 2 electron shells, whereas sodium will have, lithium atom will have 2, but lithium ion will have only 1 electron shell. But sodium atom will have 3 electron shell, but sodium ion will have only 2 electron shells. And this is the chloride ion, which is same. So this is lithium plus charge, chloride ion is there, and this one is sodium plus and chloride minus. Which one you think will have the high lattice energy, which will have a strong attraction between the ions, or ions are strongly bonded with each other? Is it lithium chloride or sodium chloride? Yeah, which one you think, in which the ions will be closer to each other? So that will be lithium chloride, because ions are smaller. So as the ions are smaller, ions will be closer. So lithium chloride will have a higher lattice energy compared to that of sodium chloride, which will have lower lattice energy. Because when ions smaller, they're closer to each other. When ions are larger, they are relatively away from each other. So the lattice energy depends on the size of the ions. So size of the ion should be small as possible. It also depends on the charge of the ions or the charge density. Example, we have lithium chloride and we have magnesium chloride, or we have sodium chloride and magnesium chloride. So when we compare, because sodium is positive, chlorine negative, here magnesium, there will be 2 chloride ions, but we are talking about only one here. So in magnesium chloride, because the charge density of a magnesium is higher as compared to that of sodium, so this will have a strong attraction, where this will have a weak attraction. So as it is a strong attraction, strong bond, there is attraction comparatively. It was weaker compared to that of magnesium chloride. That is why magnesium chloride will have a high lattice energy compared to that of sodium chloride, which will have a lower lattice energy. So the lattice energy depends on the size of the ions. It should be small as possible. That is why if we check the trend of a lattice energy down the group for chlorides, for hydroxide, example we have lithium chloride, sodium chloride, potassium chloride. So as we go down in this series, down the group, the trend, what we find that the lattice energy will decrease, or the ionic bond will be relatively weaker. But when we move across the period, so as we move across the period, we have sodium chloride, then we have magnesium chloride, then we have aluminum chloride. So the charge density is increasing. As the charge density is increasing, and the size is getting smaller. So what we observe the lattice energy will increase. So across the period, the trend is increasing, whereas down the group, the trend will be decreasing. Is it clear? The concept of the lattice energy when ions in the gaseous state result in a formation of a compound. Any doubt in this? The second part is called polarization or distortion. So what is the meaning of polarization or distortion? Normally, practically what happens, ions are not perfect spheres. Like we draw perfect spheres, we say this is a positive ion and this is a negative ion, but in reality, most of the compound this does not happen. For few compound it can, if they are isoelectronic, but not for the compounds, most of the ionic compound. So for most of the ionic compound, the negative ion is polarized, it is shifted or towards the positive ion, and that effect, this is called a polarization or distortion. And due to this polarization, what happened? As the ions come closer to each other, the lattice energy will increase. That is why theoretical lattice energies and the experimental lattice energies are different. Experimental theoretical lattice energy, we consider ions are perfect sphere. So for theoretical lattice energy, our consideration is these ions are perfect sphere. But practically, experimental data or a Born-Haber cycle will discuss how to calculate by using a Born-Haber cycle the lattice energy. So practical lattice energies will always be higher due to distortion as compared to theoretical, in which we assume, that is our assumption, that these ions are the perfect spheres. But it does not happen, there's a distortion of polarization. And due to this distortion of polarization, there is always a difference between the theoretical and experimental or Born-Haber lattice energy. Born-Haber lattice energy, Born-Haber cycle or experimental values are always higher than theoretical values. The difference between the theoretical and the Born-Haber or we can also say experimental depends on two factors. Number one, basically three factors. Number one, it depends on the size of the positive ion. That should be small as possible for causing a more distortion. So we can say small size cause greater distortion or polarization. Number two, the charge of the positive ion. So the charge of the positive ion should be a greater charge, cause more distortion or greater distortion, and that leads to a greater difference in the theoretical and practical lattice energies. And the last one is the size of the negative ion, that should be large as possible. So larger negative ions have more distortion or greater polarization. So these are the three factors on which the polarization depends. It depends on the size of the positive ion. Size of the positive ion should be smaller. Like if I say I have lithium chloride and I have sodium chloride. The chloride ion is same. So lithium chloride and sodium chloride. First thing, which will have a greater lattice energy, because this is ions are smaller, so this will have a greater lattice energy, and this will have a smaller lattice energy. That's the first thing. Now, which will have a greater, if we say about the value of lattice energy, just a number, like example, if this is 1100 kilojoule per mole, so this will be minus 900 kilojoule per mole. Negative sign shows that it is always exothermic. The second part, which will have a greater difference between experimental value and theoretical value. So if we say theoretical value, and the experimental value, that depends on the difference, that depends on the distortion, because so lithium ion is smaller in size, so they cause more distortion as compared to that of sodium. Sodium will cause distortion, but it will be a small distortion relatively compared to that of lithium, as a lithium is smaller. So when we compare, if the theoretical value was minus 1100, or say the practical value, the experimental value was minus 1100, then the theoretical value will be, and theoretical is always smaller than the experimental, as the ions we consider perfect sphere, and it will have a greater difference. For example, this is 1000. So what is the difference in the experimental value and the theoretical value? That is 100. Whereas for sodium chloride, the theoretical value, say the experimental value is minus 900, so theoretical value will be minus 890. So they will have a small difference between them. Theoretical will be higher, theoretical will be smaller, and the experimental will be higher. Here the difference is only 10. But for the lithium chloride, the difference was greater because there is a greater distortion, which leads to a greater difference between the theoretical and the experimental value of lattice energy. Is it clear? And the first part, that how the size of the positive ion affects the polarization and distortion. So smaller size positive ion cause more polarization, so they increase the difference in the theoretical and experimental value of lattice energy. Is it clear, this part? The second thing, it depends, is the charge of the positive ion. So if you have a positive ion, so we have sodium chloride, and we have magnesium chloride. Now when we compare the lattice energy, because the lattice energy depends on the size, so in this case magnesium chloride will have a higher lattice energy than sodium chloride, because in magnesium chloride ions will be closer and the charge is higher. So if we say the experimental value, or the experimental value is example minus to 2000, so this will be minus 900. Theoretical value, because now which cause a greater distortion, magnesium is smaller in size, so it will cause a greater distortion to the chloride ion as compared to sodium. So greater distortion means greater difference in the theoretical and the experimental value. So maybe that is minus 1800. So the difference in the value is equals to 200. Where this will have minus 890. So the difference in the value is only 10. Is it clear that if the charge of the positive ion is smaller and its charge is greater, then it will cause more distortion, and which leads to a greater difference between the theoretical and experimental lattice energies. And same way it depends on the size of the negative ion. If we have a larger negative ion, because the attraction is weaker, so larger negative ion will have like weaker attraction towards the electron, which leads to a greater polarization. So the polarization power of the cation increases when the positive ion is smaller and it has multiple charge. And polarizability of anion depends on the bigger the ion, the more easily it distorts, because it will have a less attraction. Now there are certain definitions which you have to learn before working out a Born using a Born-Haber cycle. First one is enthalpy of formation. What is the meaning of enthalpy of formation? When elements form a compound, we call enthalpy of formation. Atomization means when we produce atoms in the gaseous state, we call that as atomization. You have to learn, memorize these definitions. First ionization enthalpy means when electron is removed, that's called first ionization. When second electron is removed, that's called second ionization. When electron is added, that's called first electron affinity. When second electron is added, that's called second electron affinity. But first electron affinity is always exothermic because it's about bond forming, whereas second electron affinity is endothermic. Why? Because the like charges repel each other. So it is already a charge ion and it is attracting we have to add electron, that's why they repel. So we have to push this electron, that's why it will be an endothermic. Enthalpy of the lattice formation, when ions in the gaseous state form a compound, we call that as lattice energy. So these are the definitions which are important to use a Born-Haber cycle. I will just quickly mention these definitions. I'm not writing the definition, just you can work out these definitions. When What is the definition for formation, enthalpy change of formation? When element form the compound. What is the definition for lattice energy? When ions in the gaseous state, that is the condition, the ions must be in the gaseous state, result in a formation of a compound. For formation, the element must be in their standard state. It's like example, for metals, it should be solid except for mercury. For non-metals, mostly are gases, solid, but few of them, only one of them is liquid, that's bromine. So for element, it's not fixed, it depends on, from element to element it varies. So the state, what is their state at room temperature, that we consider. Then atomization means when from molecule or element in the gas in the solid or liquid state that turn into when molecule or element that turn into atom in a gaseous state, we call that as atomization. Ionization, when electron is removed, and affinity, it is when electron is added. So these are some definitions which you have to recall before using a Born-Haber cycle. So what is a Born-Haber cycle? It's just a way to find the lattice energy. So a Born-Haber cycle to find the lattice energy. So you have to learn, basically you have to learn these labels. If you learn the label, then there's no issue with the Born-Haber cycle. 4 labels you have to learn: element, atom, ions, compound. So the label, we have element, atoms, ions, and compound. How it works? What is it, how it works basically? First, element can form atoms. So if I label this as A, so what is the meaning of A? A means atomization. Because when elements form atoms, that's called atomization. So A is atomization energy. Then atoms form ions. That if I label that as B. So what is this? This is both. It is because ions can be positive ion, it can be negative ion. So when positive ions are formed, this is ionization. And when negative ions are formed, so this is actually a sum of ionization and affinity. Negative ions are formed by gaining electron, positive ions are formed by loss of electron. When ions form a compound, so when these ions form the compound, what we call that as a lattice energy. Or element directly form the compound. That's called, if we say label this as D, so D is the formation. So when we write the cycle, because where the two arrows are pointing out, that is the start of the cycle, the Hess law, and where two arrows are pointing in, that's end of the cycle. So this is the start, and this one is the end. So according to Born-Haber cycle, the overall energy change, according to Hess law, that overall energy change is independent of the root. So if we add A plus B plus C, so A plus B plus C, that is equals to D, because A plus B plus C, that's root 1, is equals to D. Or we need the lattice energy. So if we need lattice energy, that is equals to D minus A minus B. So we substitute the value, you will get the answer for lattice energy. So this is basically a Born-Haber cycle which we use to find the lattice energy of ionic compound. Is it clear, the concept of the Born-Haber cycle, how it can be used to work out the lattice energy? So first thing, you have to draw a Born-Haber cycle for different ionic compounds. First stage is that, and next stage we'll substitute the value and we'll work out. But the first stage is construct a Born-Haber cycle for sodium chloride. So we have to construct a Born-Haber cycle for a sodium chloride which is NaCl. So what should be the labels? There are 4 labels: element, atoms, ions, compound. So we should have element, and we are forming for sodium chloride NaCl. So this point we should have element, atom, ions, and compound. So what are the elements here? We have sodium, and we have chlorine. The element in there, standard state. Sodium is a solid at room temperature, where chlorine is a gas. But we don't, to form sodium chloride, we don't need 2 chlorine, we need only 1. So I should have a half chlorine molecule, because if 1 chlorine molecule, it will give 2 chlorine atoms. Here we'll have a compound NaCl. Here we need sodium atom in a gaseous state, we need chloride atom in a gaseous state, and at this point we need sodium ion and we need chloride ion. Is it clear till this point? Then I will show how it is done. We just write, this is the energy, Now, what happened? It is always step by step. First, we atomize sodium. It's not like directly, because two different elements are there. So first we atomize sodium. So sodium turn into a gas, and chlorine molecule is still there. So what is label A? The label A is the atomization of sodium, Na. Then what we did? We atomized chlorine. So the second thing, we atomized chlorine. As you can see, the arrow is pointing up. So if arrow is pointing up, it shows an endothermic change. And if arrow is pointing down, it represents an exothermic change. So because to produce atoms from element or molecule, we have to break the bond. That's why both are endothermic. So for label A and label B, arrows are pointing up. Then sodium, they are already in a gas, so we have to remove electron from sodium, and that electron should be added to chlorine. So when we remove electron from sodium, so when electron is removed, it will form sodium ion in a gaseous state, and chlorine is still atom. So when electron is removed from the atom, what we call that change? We call that change as first ionization, because we remove one electron, first electron. That's the first ionization of Na. Then this electron is added to chlorine by itself, and this is an exothermic change. So whenever there is an exothermic change, the arrow should point downward. So the direction of arrow is down. And what is this label? D. When electron is added to an atom, a neutral gaseous atom, that is called affinity, because first electron is added, and first electron affinity is always exothermic. The second, third and fourth are endo, but first is always exothermic. That's why the arrow is pointing down. Then these ions will form a compound. So this label F is there. What is this label F? This label F is a lattice energy. And then element directly form the compound. So if element directly form the compound, sorry, the sequence, I forgot to label this as E, then where will be F. So this is label E. And when element form a compound, that is called label F. So label F, when element are forming a compound, we call that energy as formation of NaCl. The element form the compound, that's called formation. When ions form the compound, that's called lattice energy. So NaCl lattice energy is E, and a formation is F. So when we use a Born-Haber Hess law, so this is where two arrows are pointing out, that is the start of the cycle, two arrows are pointing in, that is end of the cycle. So A plus B plus C plus D plus E. So A plus B plus C plus D plus E, that is equals to F. So if we need E, the lattice energy, then it will be the formation minus atomization of sodium minus atomization of chlorine minus first ionization of sodium minus first ionization of chlorine minus first electron affinity of chlorine. So we'll just substitute the value, but right now we're not substituting a value. We are constructing an equation for a Born-Haber cycle for sodium chloride. Is it clear? So the important thing what I want everyone to learn so that I can give more examples. So I want you to learn these definitions: the formation, atomization, first ionization, first affinity, second affinity, and lattice energy.